Hi, everyone. We are back for another segment discussing how to apply R in our regression framework here. We're going to build more or less on some of the work that we had talked about in a prior video. So I'm going to go ahead and load up the datasets library, and we're going to use this mtcars dataset again. And as usual, if you want to look at the details of the preloaded or pre-installed data sets in R, you just throw a question mark in front of the name of that data set, and the help documentation will show in the bottom right panel here in RStudio. And again, this is going to be useful for us when we're talking about how to interpret the regression parameters that we estimate, given that we need to know a little bit more information about the units of measurement here. So recall in one of the earlier segments, we had looked at this relationship between the miles per gallon of a vehicle in this data set, and we were trying to predict the miles per gallon by looking at the horsepower, recognizing in this scatter plot that we definitely had what looks to be here some sort of negative relationship between miles per gallon and horsepower. And you'll notice I kind of just sketched in a real quick regression line there, but it looks like that a linear regression line, a straight line, maybe does not do the best job at capturing this type of relationship between the y variable and the x variable. It may be a nonlinear relationship like this red curvy line here is a more appropriate model to consider. So what we're going to do at the beginning of this portion of this segment is we're going to talk about utilizing the natural log transformation or the logarithm transformation to transform either the x variable, the y variable, or potentially both in order to generate a relationship that is a little bit more complex in that we can capture some nonlinear behavior between the x-axis variable and the y-axis variable. So we're going to first run a model. We'll call it model 1 here. That is known as a level model. And this is the functional specification in the case where we just have a single x variable on the right-hand side. We just have our typical beta 0 intercept term and our slope, where the slope term is the usual interpretation. It's delta y over delta x. It will tell us if we increase x by 1 unit, y will go up by beta 1 units if beta 1 is positive, or y will go down beta 1 units if beta 1 is negative, right? So the interpretation of beta 1 in this particular setting here, again, in this situation, is that it is the change in y with respect to the change in x. All right, now, if we run model 1 here, we can take a look at our summary output. So let's go ahead and do that. We'll run model 1, and let me give us a little bit of space down here in the console window to look at the output resulting when we do build model 1. So here's model 1. We built it, and now we want to take a look at the summary output in the bottom panel of the console window here. And you'll notice we have our intercept estimate. And the way to interpret that in this model is if the x variable horsepower is 0, okay, then the predicted y value for our MPG variable, right, that is the model we've run here. We have MPG on the left side of the tilde of the equal sign, and we have horsepower on the right, meaning horsepower is our x variable, MPG is our y variable. So we see here if horsepower is 0, okay, and again, that doesn't really make a ton of sense in this setting, but this is how we interpret that intercept, right? The intercept term tells us the predicted value of y when x equals 0. And now you'll notice here the beta 1 coefficient, or the beta coefficient on the horsepower variable, is negative 0.06823, which is consistent with our presumption based off of our look at the diagram on the right-hand side here, right? Based on this diagram, we said, hey, it looks like there should be a negative relationship between the x and the y variable. And that is exactly what we're seeing here with this coefficient on horsepower. Now, the important thing about this coefficient, not just that it's negative, but it gives us a quantitative ability to make a prediction about horsepower's effect on MPG. Okay, and what the way we would interpret this is a 1 unit increase in horsepower will decrease the MPG variable by 0.06823. Or similarly, a 100 unit increase in the horsepower variable. So if we have an increase in the horsepower variable by 100 units, okay, then we would take this decimal point, we would move it over 2 places, 1, 2, and that would tell us we would get a reduction of about 6.823 miles per gallon. All right, so again, that coefficient on horsepower, that is corresponding to our level model here, where again, beta 1, our slope term, is just being interpreted here as delta y over delta x. So if I know how big delta x is, I multiply it by my beta 1 coefficient, right, this value on horsepower here, and that will give me the predicted change in the y variable. All right, now what we're going to do next is we're going to take a look at a few different models here where we transform one of the x or y variables. And in this next situation, which is called the level log model, okay, why are we giving it that name? Well, we have the level of y measured on the left, but we have the log of x now as our regressor on the right. So this is a linear regression model. All we've done is we've changed the x variable, we've transformed it, but note it is still linear in the betas. So this is still a linear regression model, but I'm going to argue this is a little bit richer in that it's going to capture a non-linear relationship between x and y, because the way we're going to interpret beta 1 now is going to essentially involve us thinking about x not in units change, but when we take the log of a variable either on the left or the right side, now when we interpret the beta, it's going to involve the percentage change in the variable that is logged. All right, so in the level situation, we were looking at a unit change in x, but now in the level log model in the second line, now that we have the log of x, we're going to be thinking about the percent change in x and how that affects a change in y. Okay, and we want to be careful about how to interpret this. So let me just switch my screen share here for a moment to a table that kind of summarizes the difference between the 4 variations of the level and log models that we're going to look at here. And if you look, you'll notice we've already discussed the first case in this diagram, and that first case being specifically the level model we've talked about here. Okay, and in the level model, again, we can see on the right-hand side, we have the x variable. On the left-hand side, we have just the y variable. So we're measuring the level of y on the left, the level of x on the right, which is why it's called a level model. And the way we interpret the beta 1 value here is consistent with the following. So you'll notice if we solve for beta 1, using that equation in the right column, we get beta 1 is delta y over delta x, where again, delta x is the change in the units of x and delta y is the change in the units of y. However, what we're going to see in a moment here in our second model that we're going to build called model 2, we have a slightly different interpretation. Okay, we're now dealing with a level log model where again, we have the level of y showing up on the left side, but now we're going to have the log of x, and it doesn't really matter if it's log or a natural log. I'm not going to worry about that right now. Technically, we're going to be using the natural log function here, but the log function is okay as well. And when you utilize this particular transformation, okay, we have just level of y on the left, we have the log of an x variable on the right. The way you're going to interpret the beta coefficient now is a little bit different. Okay, so we look over here, we can see that if I want to calculate the change in y, okay, we're not looking at a unit change in x anymore. We are specifically now looking at a percent change in x. Why percent change? Well, the log function has this property where it's very closely related to growth rate. So when we take the log of a variable in the regression model and we think about that variable changing, beta is going to tell us with respect to a percent change in that particular variable. And you'll notice now there was another component that's a little bit different, and that is when we want to predict the change in y, we're going to have to take the beta coefficient that's estimated from this model, and we're going to have to divide it by 100 first to figure out the resulting unit change in y that results in the left-hand side. Okay, so let's go ahead and jump back to our R code here, and we're going to take a look at running model number 2, similarly to how we had looked at the level model in model number 1. So let me go ahead and switch my screen back here to our studio. And when we build model 2, I'm going to run this line here again. I have MPG on the left, and we're going to have the log of horsepower on the right. So here is the model that we are building. All right, we have an intercept term, we have a slope term, but that slope term B1 is now being multiplied by the log of x instead of just x, which means now we're going to be thinking about the percent change in x when we interpret beta 1. The other thing I want you to note here, here are our results in the console from the level model. We had an R squared of 0.6024, meaning that model that we had built, the level model, was capable of explaining about 60% of the variation in MPG by looking at the variation in the horsepower variable. So we're going to see how the fit changes when we utilize this transformation here. Okay, so we've built model 2. Let's go ahead and run line 15. And then we're going to run the line number 16 to take a look at the summary output for model 2. Okay, keeping in mind, again, the R squared in model 1. We want to see if this fits better. And we can look at our output now for model 2. So again, the model 2 that we built here was line 15 and 16 up in the script file. And now down in the terminal window, we can see that, right? We have MPG on the left. We got log of horsepower on the right. Okay, and note that our beta 0 and beta 1 parameters have changed a little bit due to the change in the functional form of the regression model that we've estimated. So we did have these parameter estimates change. Okay, the other thing to notice though is they're still significant, right? We're getting 3 stars there, which means they're significant at 0.001 level. Those p-values are super, super small here. And that was also the case in the level model. If you just rewind the video a little bit, you can see we were getting those stars there. So this is definitely a statistically significant model in terms of the individual effects. You'll notice for the F-test for joint significance of the entire model is also significant as it was before. So we're in good shape there in terms of us having a relatively relevant model for the features that we've included to predict our Y values. But the other thing I want you to note here is our R squared has gone up. Okay, this model does provide a better in-sample fit than the level model did. In fact, it goes up from about 60% of the variation in Y explained by the variation in the X variable to 72%. So we've added, by creating a slightly more complex model using this nonlinear transformation, about an extra 12% of explanatory power in terms of our R squared metric. Now, I want to spend just a moment here thinking about how we're going to interpret the horsepower coefficient now that we have it logged. Okay, so remember what we had discussed on that slide just a moment ago. We're going to have to take that beta 1 value and we're going to have to divide it by 100. So 10.764 divided by 100 is going to give us 0.1764. So the way to interpret that coefficient here is, since we have the X variable logged, we have horsepower logged, the way to interpret this is that a 1% increase in horsepower will reduce the miles per gallon by 0.1764 units. Okay, we take that beta value, we divide it by 100 in the case where our X variable is logged. Okay, meaning if we had a 10% increase in horsepower, that would correspond to a 1.764 unit reduction in miles per gallon. So again, the change in miles per gallon is being still measured in the level of the original variable MPG, but now we're thinking about the changes in horsepower as percentage change because the log is showing up on the right-hand side and transforming that horsepower variable, creating this nonlinear effect. Okay, so it looks like Model 2 has a slightly better fit than Model 1. What we are going to do next is we're going to take a look at a third case where instead of logging the X variable, we're going to take a look at Model 3 here in a moment, which is known as the log level model, and hopefully you're thinking about what that means. And now the logged variable is going to show up on the left, so we're going to log the Y variable here, and we're going to keep just the X variable. I had a little typo there, but we're going to keep the X variable on the right untransformed. So the X variable on the right is still in just its level form, which is why this is called the log level model here. And again, now that the Y variable is transformed, we're no longer going to be thinking about the change in Y. We're going to be thinking about the percentage change in Y when we are interpreting the slope coefficient beta 1. But since X is not transformed in this case, this is going to correspond to just the change in X, the change in the number of units of X. Okay, but we're going to be thinking about the percentage change in the Y variable. So let me just jump back to my table again here so we can look at this case a little bit more closely. And again, we are now in this log level situation where our Y variable is logged on the left, but we have the level of X as our regressor or our control variable on the right-hand side. And you'll notice, again, if you go to the right column in this table here, that we do have a slightly different interpretation of how we utilize our beta 1 coefficient to predict the percentage change in Y in this model. So again, since Y is logged on the left, we're now thinking about percent changes in Y, not just the change in Y. But X is not logged on the right, so we're just dealing with delta X. And you'll notice the way we're going to have to interpret the beta in this particular situation is we're going to have to take it and multiply it by 100 before we multiply it by the unit change in X to allow us to predict the percentage change in the Y variable here. Okay, so when we have the log level model, okay, we're going to multiply beta 1 by 100 to predict the percentage change in Y. Whereas when we had the level log model, we did the opposite. We divided beta 1 by 100 in order to calculate the level change in Y from a percentage change in X when it was logged in that particular case. So let's go ahead and jump back to our R code here. And we are going to run our Model 3. So we're going to run Model 3, and we again will take a look at that summary output from Model 3. Give us a little bit more room to look here. So there is our Model 3 code. And again, you can see in the function call in the console window now, we have the Y variable logged on the left. We have the horsepower variable not transformed on the right. So again, that is consistent with this log level model specification. And again, you'll note that our coefficient estimates have changed, and that should make sense. We did transform the variable, so the estimates change. Each of these models makes slightly different predictions. Okay, again, we have statistically significant parameter estimates, both individually and jointly according to our F-test here. All p-values are real tiny. Okay, but we want to be very careful again about how specifically to interpret the coefficient on horsepower now, given that we have taken a log of our Y variable, MPG. So that horsepower variable, what are we going to have to do to it? Well, before we can interpret the percent change in miles per gallon, we're going to have to multiply that by 100. So we're going to again take that decimal point, move it to the right twice. And the way we would interpret that coefficient there would be that if we had a 1 unit increase in horsepower, what that translates to is a minus 0.34287 percent change in the miles per gallon of the vehicle. So there'd be about a 0.3% reduction in MPG if you increased horsepower by 1 unit. That is what this log level model predicts. And again, we've incorporated this nonlinear transformation here. Note also the multiple R squared is a little bit better than what it was in the level case when we did not have any nonlinear transforms, but it's not quite as good as model 2 in terms of the in sample fit here. Okay, so that is the log level model. We're going to go ahead and take a look at one more variation, kind of the fourth case when looking at these types of models, and that is a situation known as the log-log model. And hopefully you're already thinking, well, the log-log framework must have each variable log. We're going to have a log on the left and a log on the right, and that is certainly the case here. Okay, we have log of y is equal to beta 0 plus beta 1 times the log of x plus our residual. So now we have both variables log, which means each variable is going to be thought of not in terms of delta x or delta y, but in terms of percent delta x and percent delta y. So we're measuring now the changes in x and y given these transformations, both thought of as percent changes. Okay, so let's go ahead and we're going to build model 4 and we're going to run it in just a moment. But before we run it, let's jump back to our table here and make sure we can see this. So now we're in this very last situation in the bottom row where we are looking at a log-log specification here. Let's make that red. So here's our log-log specification. Note that the left-hand side variable is logged and the right-hand side variable is logged. And in this particular case, okay, we are now thinking about the changes in all the variables. The change in y is no longer delta y, it is percent change in y, and the change in x is no longer delta x, it is the percent change in x. And that means if we had solved for beta here, if we had solved for beta 1, okay, what is beta 1? Well, it's the percent change in y over the percent change in x, which you might remember from an earlier course, maybe like Econ 101 or something like that. Is related to a value or a type of metric known as an elasticity, which measures the percent change of one variable divided by the percent change of another variable. If y was our quantity demanded, for example, and x was the price we were charging, and we had data over time, we changed our prices, and we can see sales fluctuates over time, and we were to run that regression where we had the quantity of sales on the left as the y variable, and we had the price on the right, if we took the log of both of those variables and ran that regression, then beta 1 would literally be the elasticity of demand implied by our data. It's an elasticity metric here, which is units free because both y and x are measured in percent changes. So beta 1, again, in this framework, is the percentage change in y that results from a percentage change in x. So let's go ahead and jump back to our model 4 in this situation. And we're going to go ahead. We built model 4. Let's take a look again at the summary output from running model 4 down in the console window here. And when we do that, just get model 4 up there in the script window. Okay, so here is our model 4, our log-log model. And we can see the output here, right? This is our function call. We had the log of the y variable, MPG, on the left. We have also the log of the x variable, horsepower, on the right. Okay, and as usual, different type of model. This does slightly alter our parameter estimates as well as the interpretation. But again, both values, the intercept and the slope coefficient, are still statistically significant, highly. And again, the model as a whole is also statistically significant. You'll note the R squared here compared to the level model, again, is a significant increase of about 12% of an improvement in the variation in the y variable that is explained by variation in the x variable. And we also want to be careful of how to interpret here the slope coefficient beta, right, beta 1 in this model. So the way you would interpret this value here, 0.53009. Now that both the x and the y variable are logged, the way to interpret this is the following. A 1% increase in horsepower causes a 0.53009% reduction in the miles per gallon. Again, a 1% increase in horsepower causes a 0.53009% reduction in the miles per gallon. Okay. So depending on, what type of model you're looking at or what type of data you have, I think it's a really good idea to consider the role of these types of nonlinear transformations using the natural log function, especially because it gives you a nice unit-free growth rate interpretation in many cases. Before we wrap up, I wanted to just show you guys a couple other types of nonlinear transforms that you can implement in R. We did discuss the use of something called a polynomial transformation. And I wanted to show you a couple ways of how to code that in R here. So let's go ahead and do that. So model 5 here is a polynomial model, and there are a couple different ways you can code polynomial models. One way is you can write out each term individually, and you'll notice I had to put this I parentheses around it. So this is just my normal HP term on the right. And then I put a plus, and this gives me my horsepower squared term. So the regression model we're actually building here has the following form. We have y equals beta 0 plus beta 1 times x plus beta 2 times x squared, which is a nonlinear transformation of the original variable x. And again, plus our residual. So this is what we had called here a polynomial of order 2. This is a second order polynomial or a quadratic polynomial. And another way, well, actually, let's go ahead and build that model first. So we're going to build model 5 here, which is going to give us a quadratic regression model. And we can take a look again at the summary output for this model. And again, new model, we're going to get new parameter estimates. And how we interpret the betas is going to change again a little bit here, and you should be able to use some calculus. If you look at this function and you wanted to calculate dy dx or delta y delta x, what you would do is you would take the partial derivative or the derivative of that function with respect to x, and what you would get actually is you would get beta 1 plus 2 beta 2 using the power rule. And that would actually give you the partial effect of how you change x and how that affects y, both in terms of the unit change in x and the unit response in y. Okay, but again, if you're not familiar with calculus, don't sweat that too much here, but we should be able to think about how to recover that partial effect, which will depend not on 1 beta, but on 2 betas. Note that here are our parameter estimates. We're getting beta 0 is the intercept term, beta 1 is the coefficient on horsepower, beta 2 is the coefficient on horsepower squared, and these are statistically significant. And this model actually looks like it fits our data the best out of all the ones we've run so far. It's increased the multiple R squared up to about 76%, which was an improvement of about 16% variation that is explained relative to the level model, where we only had the level of x on the right. We didn't have this extra x squared term showing up. So this is a little bit more complex than the level model with just 1 x variable, because we now have 3 beta coefficients to estimate instead of 2, which means it's a little bit more flexible in fitting our data, which we can see as evidenced by the higher multiple R squared here. I'm going to show you another way of running the same model in model 5. So notice model 5, and actually I had model 6 circled below here, but they're actually the same model. Okay, but there is a different way that you could write out a polynomial model here. Imagine if you wanted a 10th order polynomial model. You don't want to have to write out all those terms on the right-hand side manually. So there's a way you can actually code this where R will generate all the polynomials for you automatically by using this poly function and then feeding it the variable you want to transform, the order of polynomial, and then we're also going to use this raw equals true here. We're going to use what's called the raw polynomial, and this again isn't a huge deal. If you don't have that set to true, if that's set to false, then R uses something known as an orthogonal polynomial, which will give you slightly different beta estimates, but the predicted values, the fitted values, will actually be the same whether or not raw is set to true or to false. So I'm going to set it to true here to show you that we get essentially the same estimates that we were looking at in model 5. Just model 6 is an alternative way to code that. So again, I want you to be mindful of these estimated values here for beta 0, beta 1, and beta 2. That was according to model 5. Now we are going to build model 6 and take a look at the summary output from doing so. Okay, so model 6. Hey, it is a polynomial regression of order 2. And again, this is an alternative way of coding model 5 here. And note the parameter estimates that we're getting. Okay, there is our beta 0, right? Here is our beta 1. Here is our beta 2. They are the same values as what we were getting in the previous model, in model 5 here. Right, if we go back up to model 5, actually let me clear what I've highlighted first, but we can go back up to model 5, and we should be able to see that that is indeed the case, that our parameter estimates are the same, right? Right here, right here, right here. That was the model 5 parameter values. Model 6, same exact estimated values. So if you wanted to make a higher order polynomial transformation, okay, you can use this poly function to do that without having to write everything out manually. There's also a way to do that incorporating interaction terms, so I'll let you guys play around with that on your own. But we're going to look at model 7 here, which is a situation where I have incorporated interaction terms, okay, between the variables. So here is the model in model 7. We have a beta 0. We have a beta 1 times x. Let's call that x1. And we have a beta 2 now times the interaction of x1 and x2, the product of x1 and x2. And the way I code that here is, again, by using that I with the parentheses, and I write the two variables inside that I want to create the interaction between. Okay, and then we have beta 3 times x2, which is our cylinder variable here. So now we're looking at the interaction between multiple variables on the right-hand side, right? Not just horsepower, but we've incorporated the number of cylinders in the vehicle as well as a right-hand side regressor here. And if we go ahead and run model 7, we can take a look at the summary output. Here is our intercept estimate. That is the coefficient on horsepower. Here is the coefficient beta 2, which is on that interaction term of horsepower and cylinders. And here is the coefficient beta 3, which is the interaction term on cylinders. And again, if you want to figure out the partial effects, how does x1 affect y, holding x2 fixed and vice versa, you're going to wind up taking the partial derivative of the regression function. Partial derivative of y with respect to x1 will give you the partial effect x1 has on y. And you will see here that that's going to involve both beta 1 and beta 2 because we have an x1 in both of those terms. Okay, so that is how you would manually code interaction terms. And again, try to mess around with that poly function to see if you can do that as well. Last but not least, model 8 involves what we call a dummy variable. A dummy variable is just a binary variable. And if you go back to the help file, you can see how the transmission variable is coded. It's either 0 or 1, depending on if it's automatic or manual. And what we can do here is we can actually write a regression with a dummy variable in it on the right-hand side. So this looks like the following, and this is actually not technically a nonlinear regression. So this is kind of the odd man out in this segment. But dummy variable, it's a binary variable, 0 or 1, and we can go ahead and build a model here if we were maybe interested in thinking about, you know, does having a manual transmission get you better miles per gallon than an automatic? So here is model 8 where we're regressing now. Oops. The miles per gallon specifically on the transmission type. Okay, and we can take a look at our summary output, and we can see here the coefficient on that transmission variable is 7.245, which means if the transmission variable increases by 1 unit, if it goes from 0 to 1, 0 being automatic, 1 being manual, then it looks like the miles per gallon on our vehicle goes up by about 7.245 miles per gallon. Okay, if the AM variable was 0, if we had an automatic vehicle, okay, then we would plug in a 0 for our dummy up here, and the predicted value of the miles per gallon would be the intercept term, saying on average in this data set, the automatic vehicles have 17.147 miles per gallon. But if we added that to the 7.245 term, then we're seeing that the manual vehicles are getting about 24.38892, right? I'm getting about 24 miles per gallon by controlling for that binary dummy variable on the right-hand side. So this was a quick look at how to take some nonlinear transformations in R and specifically how to interpret those log models, those log transformations in those 4 cases of level, log, and log models there. Hope that was useful, and stay tuned for more.